Hello everyone. Myself, Dr. Ranjith Kumar Gatla. I'm working as an associate professor in Department of Electrical and Electronic Engineering. So today I'm going to explain the subject is the power electronics, and in this power electronics course, so the first module is about power switching devices, and this is the syllabus that I'm going to cover in this module 1. So in this syllabus, mainly we are going to discuss about the thyristor, and after that the MOSFET and IGBT. So these three are the power semiconductor devices. So we are going to discuss about the power semiconductor devices, and in all these three power semiconductor devices, so firstly you will discuss the IV characteristics of the thyristors as well as the MOSFET and IGBT, and also the firing circuits of the thyristor that we will discuss. There are different types of firing circuits. So mainly in this module, we are going to discuss about the R, RC and UJT firing circuits for a thyristor, and also the gate drive circuits for the MOSFET also we will discuss, and also the gate drive circuits for the IGBT also we will discuss. And then after, the series and parallel operation of the thyristor, as well as the rating and protection against mainly the dV by dt and di by dt we will discuss, and also we will discuss the snubber circuit for the thyristor. So this snubber circuit also used to protect the thyristor, and then after that we will discuss the commutation techniques. So mainly the forced commutation techniques. There are different types of commutation techniques, especially in the forced commutation techniques that we will discuss in detail. Then in addition to these thyristor, MOSFET and IGBT, so other thyristor family devices also we will discuss. Mainly those are the triarc, GTO we will discuss, and their characteristics also we will discuss. And finally we will discuss some numerical problems based on the VI characteristics and series and parallel operation of the thyristor, as well as the VI characteristics of MOSFET and IGBT. So this is the syllabus that we are I'm going to cover in this module. Then when coming to the course outcomes mapped with this module 1, so here there totally in this course there are 6 course outcomes are there. So in out of 6, the 2 course outcomes are mapped with the module 1, and when coming to the first course outcome, which is about explain the static and dynamic characteristics of the power semiconductor devices used for power conversion in the converter circuit. So here mainly the power semiconductor devices are used in the power conversion converters. Okay, either it may be DC to AC, or AC to DC, or DC to DC, or AC to AC. So in all different types of converters, we mainly use the power semiconductor devices, or the power converters are made with the power semiconductor devices. So before going to learn about the operation of the power converter, so it is very important to know about the characteristics. Okay, that is the static and dynamic, which means the VI, and as well as the switching characteristics of the power semiconductor devices. And when coming to the Bloom's level of the CO1 is at understand level. So first it is very important to understand the static and dynamic characteristics of the power semiconductor devices to build the converter, and as well as to know the operation of the converter. Then when coming to the CO2, which is about summarize the various firing circuits and the commutation techniques useful for accurate switching function of the SCR. Yes, of course, as we know, the SCR is a semi-controlled device. So to turn off the SCR, we will use the different commutation techniques, and as well as to turn on the SCR, we use some the various firing circuits. Okay, so it is very important to discuss or to understand the various firing circuits, as well as the different commutation techniques to operate the SCR. So the CO2 is also with respect to the Bloom's level, which is the understand level. Next, when coming to the power electronics, okay, so which means the electronic devices used in the power applications, so are the which are the power electronic components. So this is a multidisciplinary subject. So here as you can see, the power electronics is related with so many other courses, okay, which we are already third some courses, and some other courses we are going to learn, okay. And the different the courses which are related with the power electronics are the circuit theory and systems and control theory, and as well as the signal processing and simulation and computation and electronics, solid state physics and electromagnetics, and power systems and electrical machines. So let me take the electrical machine subject. So in the electrical machines, if you want to control any DC or AC motor, so by using these power electronic converters, we can control, because as we can, as you already thought in the electrical machines, the control of AC and DC machines. So by changing the voltage or the input voltage, so you can change the speed of the DC machine. So how you can give the different input voltage of to the DC machine, which is by using the power electronic converter. So that is how it is the electrical machines are related with the power electronics. Similarly, in the power systems, so in power systems there is distribution. Okay, in the distribution we use the HVDC line. So in that case also we use the converters to convert from one form of energy into another form, which means like DC to AC or AC to DC. So to convert these things, we use again the converter. So like that. So these power electronics is the multidisciplinaries, okay, and then it is also the interdisciplinary in nature, right? Which means the power electronics, okay. So in the power and static and rotating power equipments, as well as the continuous and discrete control systems, and as well as the electronics device and circuits, okay. So this is also an interdisciplinary in nature, and basically the power electronics deals with some few watts of mobile charger to megawatts of the industrial drives. So which means from few watts to megawatts. So in all these applications we use the power electronics, and it is also used in variable speed drives or the battery charging equipments, which means where we need the AC to AC or DC to DC or DC to AC. In these conversions where we need, in all those applications, we use these power electronics. And mainly there are 4 different types of converters are there in the power electronics. One is the AC to DC converter, and another one is AC to AC converter, and then DC to AC converter, and then DC to DC converter. So as we know what is AC and DC means, that is alternating current, and DC is the direct current. So suppose if you want to convert the alternating current to direct current, then we can use the AC to DC converters, and which is called as a rectifier. So the function of the rectifier is which converts AC to DC. Then when coming to the second type of converter is AC to AC. So which converts, again the AC to AC converters are, there are 2 different types of AC to AC converters. One is the cycloconverter, another one is AC voltage controller. So which means the fixed AC to the variable AC. The input is fixed and the output is variable. So if you want to convert the fixed AC to variable AC conversion, then we can use cycloconverter or the AC voltage controller. And when coming to the difference between the cycloconverter and AC voltage controller, so here, as you know, unlike the DC supply, AC supply having the frequency also. So we usually the standard frequency is about 50 Hz. But as we already studied about the control of AC machines, so in the control of AC machines, by controlling the frequency also, you can change the speed of the AC machine. So like by using the cycloconverter, you can control the frequency, which means the fixed frequency, that is 50 Hz, to the variable frequency. The input is fixed frequency and the output is variable frequency. So by using the cycloconverter, you can convert the fixed AC to fixed frequency to the variable frequency. And when coming to the AC voltage controller, by using this AC voltage controller, then we can convert the fixed AC to the variable AC. So that is the function of the cycloconverter and AC voltage controller. And the other one is the DC to AC converter. So the DC to AC converter, which means the fixed DC to the variable AC. So this fixed DC to variable AC converter is known as the inverter. And then the final one is the DC to DC converters. So the DC to DC converters, which means the fixed DC to variable DC. As we know, the DC motor control by changing the input to DC supply. We can control the DC motor. So in those applications, we can use the DC to DC converters. Those are the choppers, which are also called as the DC regulators. Then all these converters are made up of the power semiconductor devices. That's why it is very important to know or to understand the characteristics of the power semiconductor devices. And when coming to the prerequisites of these power electronic course are the network analysis, because in the network analysis we will study the steady state and the transient response. Similarly, in the power semiconductor devices, when we are going to discuss about the characteristics, so in the characteristics also we have to understand the behavior of the power semiconductor device in the steady state as well as in the transient state. So based on the behavior, we will understand the characteristics. And also the power semiconductor devices. So like electronic device circuits that we have already studied. So that is also one of the prerequisites of this course, and also analog electronics also one of the prerequisites for this course. Then when coming to the power semiconductor devices, so how we can classify the power semiconductor devices? So the major, we can classify the power semiconductor devices based on different parameters. So here I have classified based on the controllability. So whether the power semiconductor device is full control or semi-controlled or uncontrolled. So here I have classified the different power semiconductor devices based on their controllability. So first here, the classification is about the uncontrolled devices. So uncontrolled devices, which are the power diodes. So here the controlling parameter is just to turn on and turn off, because here the power semiconductor devices are nothing but a switch. So the function of the power semiconductor device is just to turn on and turn off. So it will act as a switch. So then the controlling of the power semiconductor device or the switch is just to turn on and turn off, which means here the uncontrolled device, which is nothing but, so the power diode, we cannot control the turn on and we cannot control the turn off. As we know, the basic thing of the power diode, how it will conduct, if you apply the forward bias, then the power diode will conduct, and if you apply the reverse bias, then the power diode will not conduct. So which means we cannot control and turn on and turn off, right? So that is why it is an uncontrolled device. And when coming to the semi-controlled device are mainly the SCR, which we can also call as a thyristor. The SCR is nothing but silicon controlled rectifier. So here the semi-controlled, which means some extent we can control, because here the controlling parameters are on and off. Actually here the controlling is not only just to turn on, okay, the controlling is at which instant the device should turn on. That is also very important. So if it is controlled means, so not only just to turn on, so it is also at what instant you must the device must be turned on. That is also controllable. So if that is also controllable, then we can say that is the controllable. So here the semi-controlled device is the SCR. Okay, so which means only we can control the turn on of the SCR, but we cannot control the turn off of the SCR. So that's why this is a semi-controlled. Then when coming to the fully controlled devices, so there are many fully controlled devices. So which is the gate, which means gate turn on thyristor, and GTO, and then IGCT, which is integrated gate commutated thyristor, and MOS controlled thyristor, and the power MOSFET and power BJT, and also the IGBT. That is the most popular power semiconductor device in nowadays. That is the IGBT. IGBT is insulated gate bipolar junction transistor, which means in full control devices we can control turn on as well as the turn off process. That's why these devices are called the full controlled devices. So this classification is based on whether controllability, whether the power semiconductor device is full control, which means both on and off that we can control, and semi-control, which means any one of the function that we can control on or off, and uncontrolled device, which means both on and off that we cannot control. Next, when coming to the different types of power semiconductor devices, okay, so here what is that process or is controlled that I have shown here. Like we can see, first we can consider the power diode. So in the power diode, uncontrolled turn on and turn off. That's why it is a uncontrolled device. So which means the turn on that we cannot control and the turn off we cannot control. That's why it is a uncontrolled device. When coming to the thyristor or SCR, so the controlled turn on and uncontrolled turn off, which means the turn on that we can control, which means at what instant we can turn on, that is also we can control. So that's why it is a semi-control, but the turn off we cannot control. And then the power transistor, BJT, MOSFET, GTO and IGBT. These are the controlled turn on as well as the controlled turn off characteristics, which means the turn on and turn off that we can control by means of any signal. Then another thing, when coming to the BJT, MOSFET and IGBT, it needs the continuous gate signal requirement to turn on, because like unlike BJT, MOSFET and IGBT, in the thyristor, so how we can turn on? The main difference between the power diode and thyristor is, as we can see here, the symbol of the diode is like this. So here, this is the cathode and this is the anode. But when coming to the thyristor, similarly, this is cathode and anode. The extra signal that having the thyristor is the gate signal. This is the gate signal. So by using this gate signal, we can turn on the thyristor. And here, when the main difference between the turn on process of the thyristor and or the BJT, MOSFET and IGBT is, the thyristor need not require the continuous gate signal to remain turn on the thyristor. Just we need a gate signal to turn on. Once it is get turn on, we can remove the gate signal. Even though if you remove the gate signal, still the thyristor will be in the turn on position only. But in BJT and MOSFET and IGBT, it requires the continuous gate signal to turn on. So if you remove the gate signal, then the device will be turned off. That's why to turn on or to keep the turn on the device, we must give the continuous gate signal. And when coming to the SCR, that is silicon control rectifier and GTO, it needs the pulse gate requirement. That we will understand in the upcoming class when we are going to discuss about each device in detail. Okay. Then when coming to the the current flowing capability based on the triarc, which can allow the current capability in the both directions. Okay, in both directions, because here, as we can see, let me consider here, this is the diode and this is the thyristor. This diode and thyristor will allow the current flowing only in the unidirectional, that is anode to cathode. Here also anode to cathode. But unlike this diode and thyristor or other devices like MOSFET and BJT or IGBT, these triarc having the unique feature, that is it will allow the bidirectional current capability. And all other devices like SCR, GTO, BJT, MOSFET and IGBT are unidirectional capability, which means which can allow only the current in one direction. In other direction, it will not allow. So this is about some basics about the power semiconductor devices. So initially, we have classified based on the controllability, whether it is full control, uncontrolled or semi-controlled. And then after that, if it is uncontrolled, then the turn on and turn off that we cannot control. And controlled, semi-controlled means what we can control, whether it is turn on and turn off that I have mentioned here. And another one, if it is fully controlled, which means what we can control. Again here, the turn off and turn on, both we can control. That's why it is a fully controlled. And another classification is based on the continuous gate signal. So the thyristor need not require the continuous gate signal to turn on. It requires only just to turn on. Once it is turned on, even though if you remove the gate signal, it remains in the turn on position. But unlike this thyristor, when coming to the BJT, MOSFET and IGBT, it requires the continuous gate signal. When you remove the gate signal, then the device will turn off. That is the difference between the thyristor, BJT, MOSFET and IGBT with respect to the turn on process. And when coming to the unidirectional and bidirectional capability of the devices, so the only device that having the bidirectional current capability, which is the triarc, and all other devices, which means all other power semiconductor devices, having the capability of unidirectional current. Next, when coming to the history, of course, just now we have discussed the different types of power semiconductor devices. Okay, so before thyristor, it was a thyron. Okay, so which is also called as the mercury arc rectifier, or also the vacuum tube rectifiers. So this is also one kind of power semiconductor devices. Okay, so it was developed in around 1900 year. Then the first thyristor was invented in 1957. After that, the thyristor, I mean, in the thyristor itself, there are different devices that we have seen here. The thyristor family devices. Okay, like here. Okay, that is the gate turn-on thyristor and integrated gate commutated thyristor and MOS controlled thyristor. Because when the basic thyristor or the silicon controlled rectifier, so having, I mean, which is only the semi-control. So to get the full control, they slightly developed or modified the basic thyristor, so that we can utilize the thyristor in full control devices. Then the power diode thyristor in mid 1970s. Then after that, in 1980s, the power MOSFET, and now in the third phase, they developed the IGBT and the power MOSFET. So these are the most popular devices in power semiconductor devices. Then, when coming to the different applications of the power electronics, so as we know, mainly the distributed generation system. So in the distributed generation system, so the renewable energy sources we can use, because in the renewable energy sources, the most popular renewable energy source is the photovoltaic, that is a PV. So as we know, the output coming from the PV is DC. So we need, if you want to connect that DC supply to the grid, then there we need some converter. Which kind of converter? That can convert from DC to AC. So the DC to AC converter is the inverter. So in the renewable energy sources, we must use the inverter to convert the PV generated DC to AC. And then in the fuel cells and microtubes, in this case also for storage purpose. Okay, again, the fuel cell is nothing but a battery. Again, there we need the conversion of DC to AC. And like in fuel cells and renewable energy sources, we use the batteries and the superconducting magnetic energy storage devices. So in this case also, the batteries also, what is that? If you want to utilize the power from the battery to the AC appliances, then we must use the inverter. That's why in our home appliances, in the absence of power, we use the inverter. So inverter means when there is a power, the battery get charged, and when there is no power, so from the battery we will get the supply. But the battery output is DC, so we are using the inverter to convert the DC to AC, so that our home appliances like fan or light or AC, okay, of course AC may not work, but that depends on the battery capability. Okay, so like we can utilize. So that's why we usually call it as an inverter. Then when coming to the power electronic loads, usually every power converter needs some load, either maybe R or RL, but usually in the industry applications we use RLE load, which is nothing but the adjustable speed drives or the motors, which means to control. Okay, so in this way we can use the power electronics in the adjustable speed drives. Then in the transmission and distribution also, especially like in the HVDC. Okay, so because the power generating from the generating station is AC, but we are transmitting in terms of DC, and after that again we are converting into AC. So like there we need two different types of conversions. One is AC to DC, and again another one is DC to AC. So AC to DC is the rectifier, and DC to AC is the inverter. Like this, we can use the power electronic converters. So these are the different applications of the power electronic converters. Not only these, okay, there are so many applications for the power electronics, like in the industrial applications where we use the motor drives, okay, and electroplating, and for the induction heating and welding, okay, and the lighting. For all these purposes, we will use the power electronic application. So when we are going to discuss about each converter, so that time you will understand very clearly, okay, so exactly in the motor drives which type of power electronic converter that we can use, and in the induction heating which type of power electronic converter is used. Like that, we will understand clearly when we are going to discuss about each converter. Here I have just mentioned the list of the applications, and here I have shown some what is that very popular devices. Okay, I mean, to understand how the power electronics are important. Here, if you take a simple mobile charger, so as we know, the mobile charger, the function of the mobile charger is to get charged the mobile, right? So what you are going to charge in the mobile? The battery. Okay, right. So the battery charging, so which means, but input supply is AC, then you are converting the AC to DC to get charged the battery. So there we are using the rectifier. So like here, I have mentioned the different components also that you can see. The transistor for DC to AC conversion, okay, and the step down pulse transformer, and the capacitor for filtering the DC output, because from the inverter, okay, or from the rectifier, the AC to DC, okay, so you may not get the pure DC. So in that case, we will use the capacitor for the filtering purpose to eliminate the ripples or harmonics. So like there are different power electronic devices that we are using in this mobile charger. And let me consider the another example that is the most popular renewable energy, that is the PV energy. As we can see here, this is the PV panel, and from the PV panel, the output is producing the DC. So this is the DC bus that we are connecting. Then this is the battery bank. So if you want to store the energy producing from the PV array directly, then we can use the battery. So in between, you no need to use any power electronic device. But if you want to connect to a AC bus, which means some AC loads, or if you want to connect to the grid, then you must need an inverter, so which can convert DC to AC. But actually here I have mentioned the bidirectional inverter. The bidirectional inverter is nothing but AC to DC and DC to AC, which means if the PV array, okay, is producing the DC supply, and the PV array producing the DC supply, if you want to utilize to AC loads, then you need an inverter which can convert DC to AC. But then if the PV array is absent, which means at night, during the night times, okay, so there is no PV energy. So in that case, if you want to charge this battery, then in this case, of course, you are having then some AC supply, then or from the diesel generator. So this generator will generate the AC supply, and this AC supply that you can convert into the DC and stores in the battery. So in this way, we are interfacing the AC and DC by using these bidirectional inverter, which means this is a power electronic converter. This is one of the best example how the power electronic converters are important in the photovoltaic energy conversion. And next, let me take another example. Here, this is a laptop or the computer power supply system. So as we know, the laptop having the battery. So here, this is, let me represent as a battery. So this battery need charging. So here we are charging this battery with rectifier, because this rectifier converts AC to DC. Okay, so AC to DC. So because we are having the AC that is around 230 volts AC. right? The standard AC is 230 volts with 50 hertz. We are giving the supply. So from these, by using, because inside this charger there is a rectifier, and the rectifier converts AC to DC, and then we are giving the DC supply to the battery. Then the battery gets charged. Then after that, from the battery also we will get the DC supply. But here the display, here there are different components. Let me consider this is the display backlight. This display backlight needs AC supply, but here the battery output is DC supply. So here we can use inverter, which can convert AC to DC. Okay, and here the microprocessor or the power management may need the buck converter, but the voltage producing from these batteries may be high. Okay, so but these microprocessor need very less voltage, maybe let me consider the 5 volts. So in this case we are using the DC to DC converter, which means the fixed DC to variable DC. Okay, so here it may be, let me consider maybe 30 volts. So but here we need 5 volts. So if you want to step down the 30 volts to 5 volts, then we may use the buck converter. This is a type of DC to DC converter. So this is also called as a chopper. Then in the disk drive, it may need high voltage, but the voltage produced by this battery may not be sufficient. So in this case, we use the boost converter. So which means it boosts the voltage. Again, this is a DC to DC converter, which means chopper. So only in one application, that is the laptop or the computer, in one application we are using many power electronic converters, because these computer having so many devices, and the devices may need the different input supply. Some devices may need, need AC supply, and some devices need DC supply, and some devices need a particular DC supply, the low voltage or the high voltage or AC supply. So like this, based on the requirement of the components, so we are using the different types of power electronic converters. So this is also one of the best example, the applications of the power electronics and how important the power electronics. Then next example, let me consider the electric vehicle power and the drive system. Again, in the electric vehicle also, there is a battery. Okay, so we need to charge this battery. Okay, here this is the battery and this is the charger, and we need the charger. So charger is nothing but it converts AC to DC. So in all the chargers, the AC to DC converter is there. This is called the rectifier. Then the battery will charge. Then if we use the AC machines, because for wheels we connect the AC machine. So for AC machine it needs AC supply, but here the battery output is DC supply. In this way we need the inverter. And not only just to convert the DC to AC, also to control the speed. Because how we can control the speed of the motor? By controlling the speed of the vehicle, by controlling the speed of the motor only. Because the motor and the vehicle wheel is connected directly to the motor shaft. So in this way we can control, like inverter and inverter, inverter and inverter. And here there are some vehicle control systems are there inside the vehicle. Okay, like maybe air condition is there, or some sensors also we use inside, and the light. So for all these, it may need the different amount of the DC voltage or the AC voltage. So for that purpose also we use different converters. So let me consider here the DC to DC converter to boost or to buck the voltage. So that's how this is very important. The power electronic, this is also one of the best example for the power electronic applications in the electric vehicle technology. And next, in the transportation system also, in the transportation application also, we use these power electronic application. Just now we have discussed the electric vehicle. That is also one kind of the transportation application. Okay, in trains and locomotives also we use, because again to control the speed. Okay, and subways, trolley buses and magnetic aviation, electric vehicles, automotive electronics, ship power systems, aircraft power systems. In all this, wherever we need the rotation or the speed. Okay, because all these applications we use the drives. Okay, so the drive is nothing but motor plus controller. So here the controller is the power electronic controller. So this is how the power electronic applications are very huge, not limited. And even though in the space technology also we use these power electronic converters, because there also we need some computer kind of systems. Okay, so there we use, because there also need a different. It is made up of. So it is made up of different components, and different components need different voltages and different types of supply. So that's why in these applications also we use the power electronic devices. And what basically the power electronic system will looks like. This is how. So this is the power electronic converter. It may be AC or DC, which means it may be rectifier or the inverter or chopper, whatever it may be. So let me consider this is the power electronic converter, and for the power electronic converter, the input is fixed. Input source, either it may be DC or AC, which means unregulated. Unregulated means fixed. We cannot regulate. Okay. So the constant AC or the constant DC that we will give to the power electronic converter. Then the output that we will connect to the load. Okay, load is nothing but it may be drive or it may be any other device. Okay, suppose the device it required the AC supply. Okay, then we will connect what is that DC to AC converter or AC to AC converter, which means either rectifier or the AC voltage controller. Like that we will select the power electronic converter. Then how we can regulate these AC or DC supply, because as we discussed, the every power electronic converter, the input is fixed and the output is variable, which means this is unregulated and this is regulated power supply, right? Then how we can regulate this AC or DC? By using a controller. So the controller is required. So here the function of the controller is to control, because here how the power electronic converters are made up? By power semiconductor devices. All power electronic converters are made with the power semiconductor devices only. So the function of the power semiconductor device is just to turn on and off. Right, because of that, based on the turn on and off only, we have classified whether it is a uncontrolled or semi-controlled or the controlled, right? But here the controller, the controller is required to control the turn on and turn off of the power semiconductor devices in the power converters. Okay, so by controlling this turn on and turn off, then we can regulate the output voltage, which means the output supply. That is how we can control the output supply of the power electronic converter. Then how much we can control means based on our reference, which means suppose if you connect a load, okay, here let me consider this is a DC to AC converter, which is rectifier. So let me consider AC to DC, which is a rectifier. So let me consider here we are having a DC load, DC motor, and the DC motor, our reference, which means our requirement is the DC motor should run at 1200 RPM. So according to that, let me consider here you are using the voltage controller. So you have to supply the required voltage to run the motor at 1200 RPM. So according to that, you will take the reference, which means how much you have to control the turn on or the turn off of the power semiconductor device to get the required voltage for the DC motor to run at 1200 RPM. So this is how usually the power electronic system will looks like. Okay, thank you all. So this is all about, and in next session we will discuss or we will start with the basic power semiconductor device, which is the thyristor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.